Hello, everyone. Welcome back. Tonight, we are going to end our discussion on planetary systems by branching out to the other systems in the galaxy, the exoplanetary systems. So we'll talk about how we detect them, how we know about the existence of exoplanetary systems, what properties we're able to measure, and what it means for our theory about the formation of solar systems. But like always, before we start, here's tonight's quote. This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own. And that's by Giordano Bruno, who was an Italian priest back in the late 1500s. And he was actually sentenced to death by the Spanish Inquisition for his thoughts that there were worlds other than our own. Turns out he was right. All right, so detecting planets is really, really difficult. Detecting them around other stars. And there are two big technological challenges for detecting these extrasolar planets, or we'll just call them exoplanets for short. The first fact is that planets are so tiny compared to the distances between stars. So we are looking. The stars in the night sky and in the backdrop of this presentation are just points of light. We are looking for even smaller points of light or points of darkness because they're blocking the star's light. So it's just incredibly hard to see them anyway. And it's certainly not helped by the fact that stars are generally a billion times brighter than any light that is either intrinsically coming from the planet or is being reflected off of that orbiting planet. That problem is a little bit lessened if we look for planets in the infrared light, since stars don't emit tons and tons of light in the infrared, but it's not completely erased. There is still that problem. So we're looking for very tiny things, very, very far away, that are also very, very faint. And so that's why we've only been detecting exoplanets since 1995. Exoplanetary research is an extremely new subfield of astronomy and a subfield of planetary science. It's very, very new. So we're still discovering tons of exoplanets each night. We're still trying to figure out what our data is telling us about how solar systems are formed. It's still very, very new. So everything I tell you tonight, although hopefully most of it will stay the same, there are things that people are still working on. This is a very active area of research. But despite these two big challenges, we have developed some workable methods to detect exoplanets. So we can break them into two categories. We'll mostly be talking about indirect detections, but we do have actual images, actual direct detections of exoplanets, which either means we're taking images or taking spectra of potential exoplanets. So far, about 3% of all known exoplanets have been detected directly. You can see two of them here on the right. The top right one, you can see Beta Pictoris b. Beta Pictoris is the star that is being blocked out in the middle here. Beta Pictoris b is a little exoplanet, a little faint point of light you can see here. And you can also see that there's a dust disk, a debris disk around this star. So perhaps more planets are being formed. Who knows? Then down here, you can see a very good image of the star. That's the bright thing in the center, CVSO 30. And then its tiny little planet right here to the top left of the star, CVSO 30c. We label all exoplanets with a lowercase letter next to the star's name, telling you when, how, in what order they were discovered. So perhaps CVSO 30c, perhaps CVSO 30 has another planet that's not visible in this image, 30b, but 30c is the one that's visible here. Most of the exoplanets we've detected have been through indirect detections, where we are essentially saying there's a planet there without actually having seen the planet. 97% of the known exoplanets we've detected have been detected indirectly. And that's what we'll talk about tonight, the three big detection techniques to look at exoplanets indirectly. And so there are, so those three are radial velocity, what we'll call here tonight the Doppler method, astrometry, which is measuring the precise positions of objects in space, and then transits as well. Here on the right, you can see a plot that I've made with current exoplanet data, where we've got orbital period in days, how long it takes for a planet to orbit its star on the horizontal, and on the vertical, we got the mass in Jupiter masses. And you see I've color-coded things by detection method. So radial velocity, or the Doppler effect, is in this nice light green. There's a big cluster of it to the top right. Transits, where we are observing changes in the star's brightness when it passes in front of the star as seen from Earth. We've got two nice clusters of purple there. Astrometry, just like the Doppler effect, is detecting some subtle gravitational effects caused by orbiting planets. It's in a nice orange. There's a small cluster of them at the very top right. And then these dark blue points, these are our own planets. So Mercury and Mars are not visible. They are too of low mass. They're below 10 to the minus 3 Jupiter masses. So these 2 points are Venus and Earth. Then here at 1 Jupiter mass is obviously Jupiter, Saturn, Uranus, and Neptune. They're both behind the legend there. So you can see we're detecting a lot of things around Jupiter masses. A lot of smaller things too, but so far not much that is of the same mass and orbital period as Venus and the Earth. That's something that we'll talk about in a little bit. So let's get into these 3 indirect detection techniques in more detail. Before we do that, I do want to just briefly review the concept of the center of mass. So remember that the planets don't actually orbit their stars. More specifically, everything in that system orbits the system's center of mass. So let's consider Jupiter, just the sun and Jupiter. So Jupiter's most massive planet, but the sun is still 1,000 times more massive. As a result, the center of mass between the sun and Jupiter lies about 1,000th of the way from the center of the sun to the center of Jupiter, putting it just outside the sun's visible surface. In other words, what we usually think of as Jupiter's 12-year orbit around the sun is really a 12-year orbit around the center of mass. And because Jupiter and the sun are always on opposite sides of the center of mass, the sun must orbit this point with the same 12-year period. So here's a little animation I rigged up, greatly exaggerated. We've got Jupiter on the outskirts, the sun in the middle. And you can see that although this is greatly exaggerated, they are orbiting a point outside the sun. But obviously, we don't actually tend to notice the sun's motion because its average orbital distance is barely larger than its own radius. Nevertheless, with precise measurements, extraterrestrial astronomers could detect this orbital movement of the sun and thereby deduce the existence of Jupiter, even without having observed Jupiter itself. They could even determine Jupiter's mass from the orbital characteristics of the sun as it goes around the center of mass. And a more massive planet at the same distance would pull the center of mass farther from the sun's center, giving it a larger orbit. Because the sun's period around the center would still be 12 years, the larger orbit would mean a faster orbital speed around the center of mass. So because the planet is tugging on the sun gravitationally, we can measure that little wobble and deduce the existence of a planet around that particular star. And in fact, if we were to look at the system edge on, this little bottom one actually shows us what we might see the star doing, just kind of wobbling back and forth. We wouldn't actually see the planet, we just see the star doing that. And that looks kind of weird. We would probably investigate it further and say, hey, there might be a star, there might be a planet orbiting that star. Now you'd have to do this over many years. Jupiter has a 12-year period, but for instance, Saturn has an almost 30-year period. So you'd have to be viewing the sun for 30 years before you were able to conclusively say, there's a planet orbiting the sun with a period of 30 years, therefore it must be Saturn. And you can even go out further. Neptune has a period of a little over 150 years. So you have to observe the sun for over a century to deduce the existence of Neptune. So you can see the problems we're going to start to face when we're just relying on the gravitational tug and the slight wobble of the star caused by that orbiting planet. And so let's get into the astrometric method. Astrometry means measurement of the star. So if we measure stellar positions over time, we might find some slight wobbles in the star's motion around its average position. So, for example, this image of the top right shows the calculated wobble in the sun's motion through the sky, which is the straight dashed line, caused by Earth tugging on the sun. And that's the loopy line. So as the Earth goes around the sun, if we were to, from another planet, around another star, watching the sun move across our sky, it will do this little loop. And we could deduce the fact that Earth exists around the sun. But there are some limits to this method. These changes in the star's position on the sky are so very small. So, for example, from a distance of 10 light years, a Jupiter-sized planet in a Jupiter-like orbit would cause its star to move slowly from side to side over an angular distance by only about 0.003 arc seconds. That's very tiny on the sky. At double the distance, the observed motion would be only half as large. And at 10 times the distance, 100 light years away, it would be only 1/10 as large, so 0.0003 arc seconds. And so for this reason, the astrometric method is really only useful for massive planets around relatively nearby stars. And just as I illustrated with, if we want to deduce the existence of Neptune, we're going to have to watch the sun for over a century. Depending on how far away the planet is from the star, it might take actual decades or centuries for this motion to be completely observed and for us to be completely sure that there's a planet causing that wobble in the star's motion across the sky. So the astrometric method really only works for massive planets around relatively nearby stars that are also orbiting relatively close to their star. And so only on the order of tens of exoplanets have been detected this way. This method is really more useful for deducing the existence of binary and multiple star systems instead of planetary systems. But you can use it, and we have detected on the order of tens of planets today. And the new spacecraft Gaia, the European spacecraft, is really helping us add more exoplanets to the astrometric method category. The other way to look at wobbles is to look at the Doppler method. So remember, we talked about the Doppler method several weeks ago. The Doppler effect is measuring the change in the light coming from a source, a star in this instance, where everything will be blue shifted. A star spectrum will be blue shifted when it moves towards us, and red shifted when it moves away from us. This allows us to measure the star's orbit relative to its center of mass, allowing us to then deduce that a planet exists. So, in fact, this is the way the first exoplanet ever discovered, 51 Pegasi b, back in 1995 was discovered. And in fact, here you can see this is known as its velocity curve. So we've got the time in days on the horizontal and the velocity in meters per second of the star, 51 Pegasi, where 0 is its average velocity. And you can see there's some deviations by about 50 meters per second either way. And that will tell us that there must be a planet orbiting this star. So we can see that it has a 4-day period measuring from trough to trough here. There's about 4 days. That tells us the planet's orbital period. So this planet must be very close to its star to complete an entire orbit in just 4 Earth days. The Doppler data also allows us to determine the planet's approximate mass, because a more massive planet has a greater gravitational effect on the star, and therefore causes the star to move at higher speed around the system's center of mass. So the velocity change from -50 to 50 meters per second tells us the star's orbital speed, which gives us the planet's mass. In the case of 51 Pegasi, the data showed that the planet has about half the mass of Jupiter. And because this is a kind of a Jupiter-sized planet orbiting very close to its star, we call these types of planets hot Jupiters. And we have found a lot of hot Jupiters. We'll talk about what that means for our theory of our solar system formation towards the end here. Current techniques can measure a star's velocity shift to a fraction of a meter per second, corresponding to a Doppler wavelength shift on the order of 0.0000001%. As of tonight, roughly 918 planets have been detected through this method, which is about 20% of all exoplanets detected. But there are some limitations to this method. So just like the astrometric method, once again, this works for really big planets, really massive planets like Jupiter, orbiting very close to their star, because that means it's going to have a stronger gravitational tug, and we can actually observe these Doppler shifts happening on a reasonable time scale. If it's going to take several human lifetimes to observe it, then it's going to be really hard to observe it. If it's just going to take a month or two, we got it. But also, the Doppler effect does require a relatively large telescope and large exposure time, because we're measuring the spectrum of the star and deducing a shift in the spectrum. So we got to take a spectrum of a star, and that's going to require large telescope, long exposure time, with just the right resolution to deduce that motion. This is a more time-expensive technique. The less time-expensive method does not rely on detecting the gravitational tugs between a star and a planet, but instead relies on the fact that about 1% of stars that we see in the night sky with orbiting planets have their orbits aligned, so that as we look towards that star's planet will pass in front of and behind the star, causing these slight dips in the total brightness of the system. Here's a little NASA animation illustrating the idea. So as this planet comes in front of the star, you can see the light curve down at the bottom left. It will block some of that star's light, creating a dip in the light curve. That dip could only be caused by a planet. So we can infer the existence of a planet by watching a lot of stars, seeing if they dim a bit, and then saying that's a planet, that's caused by a planet. Most exoplanets we've detected are transit exoplanets. About 72% of all planets detected have been through the transit method. It's a very, very useful method that allows us to just watch a section of the sky or the entire sky and just watch for little changes in brightness. And we're talking very, very small changes in brightness here. It's not going to, suddenly dim by half. It will dim by like 0.1% maybe. Just like the Doppler and the astrometric methods, there are benefits and limitations to the transit method. So the transit method really only works for stars with their orbital planes aligned so that we see them edge on from Earth. If the planet was going around like this with the star in the middle, transit method isn't going to do anything for us. It's got to come in front of and behind the star as viewed from Earth. But it also suffers from the same biases that the astrometric and Doppler methods suffer from. It's really only good for finding planets with very short orbital periods. So once again, we got to do this on a human time scale. Perhaps if we have been going at it for longer than since 1995, we might find more planets with bigger orbital periods. But as of right now, we're stuck with sort of these small orbital periods. However, here we don't need the planets to be massive. We can find planets much smaller than the Doppler or the astrometric method. So for instance, the satellite Kepler, which was the big satellite that detected all of these transit planets, they were able to measure the dimming of just 1/100% of a star's brightness, which corresponds to planets smaller than Earth. So here you can see all of the transit exoplanets. We've got orbital period in days, once again on the horizontal, and planetary mass and Jupiter masses on the vertical. And everything is color-coded, and you see the color bar on the right, by planetary radius in Jupiter radii. So we've got a cluster of some Jupiter-sized planets, which is relatively easy to detect. But then we've got a much more dispersed cluster of smaller planets, maybe not exactly Earth size, but smaller than Jupiter. These two purple squares at the bottom are Venus and Earth. So once again, we're still not getting down to this section over here. That's still on the frontiers of exoplanetary research, but we are detecting much smaller planets here with the transit method. All right, here's your first question of the night. Which detection method or methods, there are multiple correct answers here, measure the gravitational tug of a planet on its star, allowing us to estimate planetary mass? A, the transit method, B, the astrometric method, or C, the Doppler method. So take a moment, figure out what your answer is, and come back. The correct two answers are the astrometric method and the Doppler method. The transit method tells us nothing about an exoplanet's mass. All right, now let's talk about what properties can we measure from exoplanets. So we can get a lot of orbital properties. So all three methods allow us to learn a planet's orbital period. So the astrometric method allows us to measure the star's orbital motion around its center of mass. So the planet's orbital period must be the same as the star's. The orbital period from the Doppler method is just the time between peaks in the velocity curve, like I showed you before. And the orbital period for transiting exoplanets is just the time between repeated transits. And then you can get an orbital distance straight from Kepler's third law. And so we're able to know the orbital situations for many, many exoplanetary systems. So for example, this was in the news a few years ago, this system, the TRAPPIST-1 system, and it was discovered via the transit method. The system consists of 7 terrestrial planets that are orbiting a red dwarf. You can see the red star here with a yellow dotted outline as sort of indicative of the sun size would be on the scale. And all 7 of these terrestrial planets, if you see the inset here, all orbit at distances closer than Mercury is to our sun. Furthermore, the planets B, C, E, F, and G are all similar size to Earth. And the planets E, F, and G are also in that star's and TRAPPIST-1's habitable zone, which means there could be liquid water on those planets. So this is very, very cool. We don't find a lot of exoplanetary systems with as many planets as we have, but that's not a statement about the true nature of the universe. It's probably due to the biases inherent in our detection methods. But it was very, very cool to see a multi-planetary system with 3 planets in the habitable zone around their star. So very, very cool system. That we got all this information about it from the transit method. We can also measure a planetary orbit's eccentricity from the Doppler and astrometric methods. Remember, eccentricity is how elliptical a planet's orbit is. So Earth has an eccentricity very close to 0. It's almost a perfect circle. Mercury has an eccentricity that is much higher. It is a much more elliptical orbit. So here you can see a bunch of velocity curves for 4 different planets. And we can see a few key things about these planets. So the top left one, HD 4208b, this is around a sun-like star with a planet that is about 8/10 of the mass of Jupiter in a nearly circular orbit at an orbital distance about 1 2/3 astronomical units. And you can see that it's not very massive because the peaks aren't huge, and it takes several days. So that's how we get an orbital period out of it. Top right, the planet HD 10697b, way more massive planet. In a very similar orbit, the period is the same, but the amplitude of these waves is larger, so we know it must be a much more massive planet. The bottom left, HD 27442b, Similar mass, but in a closer orbit. So the waves are closer together. So about 8/10 of a Jupiter mass, but in a closer orbit because the waves are closer together. Meanwhile, at the bottom right, HD 187085b, we've got a planet in a way more eccentric orbit. So we see this asymmetric Doppler curve, a velocity curve, which tells us that the star's speed varies greatly through its orbit, which indicates a more eccentric or elliptical orbit. So that's how we get all that kind of information out of Doppler and the astrometric methods. We can also get physical properties of known exoplanets, not just what their orbits are like, but we can tell what their masses are. Because both the astrometric and the Doppler methods measure gravitational tugs on the stars caused by the planet, so we get masses from both of those methods. However, the Doppler method, it's tougher. There's a caveat here. Because remember, the Doppler method only tells us about motion towards or away from us, not motion, side to side that doesn't vary along our line of sight. So if the planet orbits face on along our line of sight like this with the star in the center, then we don't detect a Doppler shift because the star isn't moving towards or away from us. So the Doppler method only tells us a star's full velocity if the planetary system was completely, precisely edge on. But very few planetary systems are precisely edge on as viewed from Earth. So in reality, planetary masses for the Doppler method are really more like lower limits. But combining the Doppler method with the transit method will give very accurate masses. And we don't have to worry about this caveat with the astrometric method. In fact, the transit method is also the only known way to measure an exoplanet's size, where the more starlight a planet blocks, the bigger the planet must be. So here on the right, you can see the 6 planets in the Kepler 11 system, where on the horizontal for all these plots, we've got the time relative to the maximum transit in hours. And on the vertical, we've got the percent of light blocked by the planet from the star. So you can see that planet B, this yellow line, dips just a little bit. It doesn't block a lot of light from the Kepler 11. So it must be a relatively small planet, only about twice the size of Earth. Meanwhile, let's see, this green curve, planet E, that green curve dips a lot. And so it must be much bigger to block that amount of light. So it must be about 4.5 times the size of Earth. So we can learn the size only from the transit method. And if we know the planet's mass from the Doppler method or even the astrometric method and the size from the transit method, we can get densities, which is very important for us to understand the general characteristics of these planets. So here, for example, is the how we calculate the density of the planet Kepler 10b. So here we've got the velocity curve from the Doppler method. We'll remember the amplitude of this curve gives us a mass, so it's about 4.5 times the mass of the Earth. We've got the light curve from the transit method, where it blocked just a little bit of light, so it must be relatively small, only a little less than 1.5 times the size of Earth. Density is just mass divided by volume. Assuming this planet is a perfect sphere, we can get a density of about 8.8 grams per cubic centimeter. That is way more dense than Earth. Meanwhile, other planets, we get densities of around 0.3 grams per cubic centimeter, which is even lower than that of Saturn, which is the lowest density planet in our solar system. So extrasolar planets come in a way more wide variety of types than just the planets in our own solar system. We can even get a handle, some estimates of what these planets' atmospheres must be like. So by looking in the infrared part of the electromagnetic spectrum, we can, where remember, stars don't emit a lot of their light, only planets really do. We can determine what types of molecules are in their atmospheres, like greenhouse gases that absorb infrared light. So for instance, the planet HD 189733b has water vapor in its atmosphere, while HD 209458b has methane, hydrogen, sodium, and a few other compounds. During eclipses, when the planet is passing in front of and behind its star, we can get just the total light from the planet by subtracting out the star's light, which gives us an estimate of the planet's temperature. So, for instance, the planet HD 189733b has a cloud top temperature of 1100 Kelvin, or just over 1500 degrees Fahrenheit. And even more detailed observations can actually be made of some planets to create weather maps. So this is the atmospheric temperature map of HD 189733b. I know we need to come up with more creative names for some of these planets. But you can see how the temperature varies between the day side and the night side. During the day side, it reaches 1200 Kelvin at night. 900 Kelvin is clearly more cold at the poles. So we are starting in more recent years to get a handle on the atmospheric compositions and temperature of these exoplanets, which is very, very, very cool. So here's your final question for the night. Which one of the following can the transit method tell us about a planet? A, its mass, B, its size, or C, the eccentricity of its orbit? There is only one correct answer this time. Right, and the correct answer is its size. We can't get a mass or eccentricity from a light curve, only the size of the planet. So now, how do exoplanet properties compare to our solar system? So when we look at their orbital properties, here I've got a plot of current exoplanets, where we've got average orbital distance in astronomical units on the horizontal, and then the orbital eccentricity on the vertical, and the sizes of the blue points tell you about their estimated masses. So the biggest points are greater than 10 Jupiter masses. The smallest points are less than 100 of a Jupiter mass. And let's give you some context here. The red points are the data for our own solar system. So this red point that the arrow is pointing to, that is Earth. At 1 astronomical unit at nearly 0 eccentricity. This point is Mercury, the most eccentric planet in the solar system. So you can clearly see that many of the known exoplanets orbit their stars much more closely than Mercury orbits the sun. And very few are located as far from their stars as the gas giants are in our solar system. These last 4 red points, those are the gas giants, Jupiter, Saturn, Uranus, and Neptune. And there's not many out here. Many of these planets also have very large orbital eccentricities, getting even bigger than Mercury to have these really, really, really elliptical orbits. Meanwhile, our solar system is full of pretty circular, relatively circular orbits. That's one way that exoplanets differ from us. In terms of their physical properties, the Kepler mission has detected so many planets that we're actually able to start doing statistics on exoplanets. And although it comes with a lot of biases, a lot of assumptions, this number gets revised in every exoplanetary statistics paper that gets published. We are able to estimate the proportion of stars with planets. And we found that planets are common. There is at least 1 planet on average per star. So you go outside tonight and look up in the night sky and point to any star, it is likely that you are pointing to a star that has a planet in orbit around it. And 1 in 5 sun-like stars have an Earth-sized planet in the habitable zone where liquid water and then potentially life could exist. So here you can see a plot of different habitable zone planets. Venus is just outside our habitable zone. Mars is just in it. Earth is definitely in it. And then a bunch of exoplanets that we think are relatively habitable. Currently, tens of exoplanets have been found in the habitable zones of their stars. So having a planet around a star is not as odd. It's not odd at all. In fact, it's pretty average. We also see that small planets seem to outnumber large planets by a significant margin. So here we have orbital period in days on the horizontal, planetary radius, this time in Earth radii on the vertical. Where obviously 1 is Earth, 4 is about Neptune, 10 is about Jupiter. And the 20 is just bigger to fit these bad boys in here. You can see the 2 red dots, that's Venus and Earth. And so we can see there are distinct groups of planets here on this diagram. We've got up here, these are the hot Jupiters. These are Jupiter-sized, Jupiter-mass planets orbiting very, very close to their host stars. You can see there, it takes them between 1 and 10 days to complete an orbit around their star. There's a smaller cluster over here, which are cold gas giants, much more like Jupiter and Saturn in our solar system, although still relatively close at Venus and Earth's orbits. There's a hazy group full of ocean worlds and ice giants, places like Uranus and Neptune. There's a big cluster of rocky planets. Super Earths is what they're sometimes called because they're just slightly more massive or slightly bigger than Earth. And then lava worlds, where these are rocky planets about an Earth size, but extremely close to their host star, just boiling, molten rock all over there. But you can see there is this sort of frontier area where we are working hard to detect true Earth-like planets. It's just takes more than what we've got right now. We are working hard on that problem, though. So don't think that the lack of any blue points down here means there are no Earth-sized planets. It is probably a bias of our detection method, so we are working to overcome those biases. We can also see that there's way more variety in our own planets. So here we've got planetary mass on both the top and bottom horizontals. On the bottom horizontals in Earth masses, on the top it's in Jupiter masses. And on the verticals, we've got the planetary radius. On the left vertical, it's in Earth radii. On the right vertical, it's in Jupiter radii. And so any point on this plot is actually a measure of density. That's what these 3 dashed white lines tell us. The leftmost is about the density of styrofoam. The middle is about the density of water. And the rightmost is about the density of lead. Once again, the red points are our planets in our solar system. Where all the way down to the left is, I believe, Mars, then Venus and Earth, Neptune and Uranus, Saturn, and then Jupiter is the rightmost red point. So you see there are tons of these puffed up, low density hot Jupiters, maybe some water worlds around where Uranus and Neptune are, a few, maybe some rocky planets. There's tons and tons of variety of planets here that we just don't have in our own solar system. So how do we explain this wide variety of planets when we look at our theory of solar system formation? So in particular, hot Jupiters were a big problem when we first started detecting exoplanets, because these are gas giants that orbit very close to their star. And remember, gas giants shouldn't be forming anywhere near their stars. They should be forming in the cold outer regions where there's tons of gas for them to accrete and build up to their giant sizes. So our current theories about it is that they were formed in the outskirts of their solar systems, just like what we expect, but then migrated in, probably caused by these gravitational perturbations in the original nebular disk, where either some friction from the dust and gas in the disk caused them to lose some orbital energy, or maybe as they were forming, they pulled gas in front of them behind them, and that extra little bit of concentrated gravity pulled them slightly in. It's still a working theory. We're still testing it. We're still figuring out how these hot Jupiters exist, but we're pretty sure we do not have to toss out the nebular theory of solar system formation. We're pretty sure we can figure this one out. However, we still can't fully explain the wide diversity of planetary types we see, although there are possible explanations. So, for example, hydrogen-rich extrasolar planets vary in density by a factor of about 100. a range far greater than the density range we see in our own solar system. But it seems reasonable to think that much of this range is attributable to increases in temperature caused by some Jovian planets orbiting very close to their stars. That heating may pump up their atmosphere to large sizes and thus low densities, although models can't accommodate for the full density range we see. Similarly, the lack of water worlds in our own solar system may not be that mysterious. Water worlds may be similar to Uranus and Neptune, although in some cases much smaller. These worlds may be much like the ice-rich planetesimals that seeded the formation of gas giants in our own solar system. In that case, perhaps whether water world planets exist depends on when a star clears its nebular gas, halting the epoch of planet formation. In our solar system, this didn't occur until the ice-rich planetesimals pulled in vast quantities of hydrogen and helium gas from the solar nebula. Perhaps in other systems, an early solar wind blasted out the hydrogen and helium gas before it could be captured. So there are some tentative explanations for this wide variety of planets that we see around other stars, although we are still working. Like I keep saying, this is a very, very new field of research. It's very active, and there's a lot of thinking happening here. So that is where we'll end it. A little shorter tonight. I don't want to get too deep into exoplanets because a lot of it is still very new. Over the next 3 weeks, we'll be taking a break from talking about astronomy and go into physics and talk about relativity, both the special and general theories of relativity, and then go to the subatomic realm and talk about sort of the building blocks of our universe before getting to stars, galaxies, and the universe. So let me know if you have any questions down below. Make sure to like, comment, and subscribe, all that fun YouTube stuff. And I will see you all next week.